In this second video, we're going to look at a few examples of complex functions and also study the triangle inequality. As a recap of the previous video, we looked at the need for complex numbers as required for the fundamental theorem of algebra. We looked at the Cartesian and polar representations of complex numbers. We studied Euler's formula, a very important formula in maths, and de Moivre's theorem, and how to use those to manipulate trigonometric functions. We also looked at a geometric interpretation of complex multiplication, namely scaling and rotation in the complex plane. The intended learning outcomes for this video are given here. You should be able to use the operation of complex conjugation. You should be able to apply the triangle inequality in order to set bounds on sums of complex numbers. You should be able to manipulate trigonometric and hyperbolic functions. And lastly, you should be able to calculate the roots of complex numbers, taking account of the multi-valued nature of complex numbers. Right, let's begin.
We're going to begin by looking at complex conjugation. Now, we define the complex conjugate of some complex number z by flipping the sign of its imaginary part. We describe complex conjugation by some function f acting on a complex number z, and we denote it using a star. And effectively this means that we replace plus I by minus I. Taking some complex number z, written as x plus iy, its complex conjugate, z star, is given by x minus iy. We can draw this in an Argand diagram to see what's going on. Real and imaginary. So let's take some input complex number z, described by this vector, and it has real part x and imaginary part y. When we take the complex conjugate, we flip the sign of the imaginary part. So we're now down here at minus y. And the resulting number, complex number, z star, is described by this vector. From this, it's easy to see that complex conjugation is given by a reflection in the real axis. Let's see what happens if we multiply z by its complex conjugate. We have x plus iy times x minus iy. If we multiply this out, the cross terms cancel, and we end up with x squared plus y squared, which we know from earlier is the modulus squared of our complex number, which is real. We can also think about this in modulus argument form. So we can write z equals r e to the I theta. And if we take the complex conjugate, the length of the vector r doesn't change, but its angle with respect to the real axis changes sign. If we then take z times z star, we end up with r squared, and then theta minus theta gives us 0. So we just end up with r squared, as we did for expressing the complex numbers in terms of x and y. There's an important point to make about principal values of the angles in the complex plane. So if we have the complex number z is e to the I pi by 4, which in this diagram would mean that this angle here is pi by 4, then its complex conjugate, z star, would be described by e to the minus I pi by 4. This is a perfectly okay way of writing this complex number, But you'll recall from the first part of this topic that we are restricting ourselves to theta lying between 0 and 2 pi. So we can therefore, without changing the number itself, but only changing its argument, add 2 pi times I to the argument, and we end up with e to the 7 pi I by 4. So here theta is 7 pi by 4. And that falls within our principal values that we're restricting ourselves to. In general, the complex conjugate of some expression is the same as that expression applied to the complex conjugates. And this is easiest to show with a couple of examples. So consider taking z squared and then taking the complex conjugate. What this means is that this is equivalent to taking the complex conjugate and then squaring. We could also consider taking the complex number z, multiplying by I, and then multiplying by some real number, x, taking the complex conjugate, and this will be the same as x, which is its own conjugate because it's real, times minus I, which is the conjugate of I, times z star. And as a final example, we can think about I to the power of z complex conjugated. And you can show that this is minus I to the conjugate of z. And I encourage you to work through these by letting z equal x plus iy and just checking that these all make sense. Armed with the complex conjugate, we can also show that the real part of z, in other words x, is given by a half lots of z plus z star. And similarly, the imaginary part of z, in other words y, is given by 1 over 2i lots of z minus z star. We can also use the complex conjugate to write the modulus as the square root of z times z star, and the argument of z, you can check for yourselves, is given by 1 over 2i times the complex logarithm of z divided by z star. And just a quick note that we will revisit the complex logarithm in quite a lot more detail over the rest of this course. Complex conjugation also gives us a way of dividing complex numbers. Consider dividing the complex number z1 by another complex number z2. What we can do is we can multiply this by z2 star over z2 star, because this fraction evaluates to 1. But crucially, on the denominator, we now have z2 times its complex conjugate, which is a real number. So carrying on, we now have z1 times z2 star over the modulus of z2 squared. We also get a little more information if we think about this in modulus argument form. So also note that if we let z1 equal r1 e to the I theta 1 and z2 equal r2 e to the I theta 2, then z1 divided by z2 is r1 e to the I theta 1 over r2 e to the I theta 2. Now the moduli are real numbers, so they divide as normal. And the arguments of the exponent give us θ1 minus θ2. From this, it's easy to read off that the modulus of z1 over z2 is simply r1 divided by r2, which is the same as mod of z1 over mod of z2. And also the argument of z1 over z2 is given by θ1 minus θ2, which is the same as the argument of z1 times z2 star. And we can also write this as simply the argument of z1 minus the argument of z2. Next, we're going to look at the triangle inequality. This is a very important relationship that's useful for establishing bounds. We begin by looking at the modulus of a complex number z. This is given by the square root of the real part squared plus the imaginary part squared. Now x squared and y squared are both real positive numbers, and so we know that this quantity is greater than or equal to the square root of x squared, with equality if y equals 0 and z is a purely real number. Now x is just the real part of z. So this relationship says that the real part of z is less than or equal to mod z, with equality if z is real. Now we can use this relationship to find an inequality on the sum of two complex numbers. Now consider the squared modulus of z1 plus z2. We know that we can write this as z1 plus z2 times its complex conjugate. We can take the complex conjugate inside the brackets. So we have z1 star plus z2 star. And multiplying this out, the first term will give us mod z1 squared. z2 times z2 star will give us mod z2 squared. And it turns out, and you can check for yourself, that the cross terms give us 2 times the real part of z1 z2 star. Using our inequality from above, we know that the real part of z1 z2 star is less than or equal to the modulus of z1 z2 star. That means that we can write this inequality Finally, we can simplify this last term by noting that, as before, these terms are unchanged, but then we can separate this as the modulus of z1 times the modulus of z2. And that allows us to factorize this as mod z1 plus mod z2 squared. Now, if we compare what we started with up here with what we ended with here, we can now write the inequality, the mod of z1 plus z2. So we're taking the square root of the terms I underlined in blue, is less than or equal to mod of z1 plus mod of z2. This is the triangle inequality. And it's so important, I'm going to put a red box around it. Pictorially, what does this mean? Let's draw ourselves a set of axes. We have real and we have imaginary. And let's consider Z1 as being this complex number and Z2 as being this complex number. Taking the sum of these two complex numbers, which we know is a vector sum, means we can add Z1 and Z2 top to tail. So the resulting vector is going to lie along here. This is Z1 plus Z2. And what this inequality is telling us is that the length of the purple vector is at most the length of the blue vector plus the length of the green vector. And this inequality is saturated if the argument of Z1 equals the argument of Z2. In other words, their vectors are collinear. It turns out we can iterate this result. And we find that the modulus of the sum of a collection of complex numbers is bounded by the sum of the individual complex numbers moduli. We know that we can often think of integrals as the limit of sums, and it turns out that if we have the integral of some complex function f of z dz, the magnitude of the resulting complex number is less than or equal to the integral of mod f of z dz. We will use this relationship later in the course when we're interested in bounds. We're now going to look at trigonometric and hyperbolic functions and how they are related through complex numbers. We have Euler's formula, which states that e to the I theta is cos theta plus I sine of theta. What about if we consider changing the argument from theta to minus theta? This gives us e to the minus I theta. Now cos is an even function, so cos of minus theta is just cos theta. Sine is an odd function, and so we get minus I sine of theta. This allows us to rewrite cos theta is a half e to the I theta plus e to the minus I theta, and sine theta is 1 over 2i e to the I theta minus e to the minus I theta. And you can use the same manipulations to show, for example, that cos of n theta is a half e to the I n theta plus e to the minus I n theta. We can compare these to the hyperbolic functions. The hyperbolic functions are cosh of x is a half e to the x plus e to the minus x, and sine of x is a half e to the x minus e to the minus x. Now, we're now going to make an assumption about the exponential function. I'm going to write down our assumption, and we're actually going to prove this assumption later on in the course. We're now going to assume see later that e to the x may be extended to complex arguments. In other words, things like e to the z, where z is complex. It turns out that the expressions above for hyperbolic and trigonometric functions are still valid for z, for complex z. And to give you an idea of why we're allowed to extend to complex arguments for these trigonometric, hyperbolic, and exponential functions, it turns out that the power series expansions of these functions that we talked about in the previous part for sine and cos, they still hold for complex argument z. Now, taking this assumption, let's try setting z equal to ix. Now, with this assumption, let's try setting z to I times x, where x is real. Now, let's look at cos of z. What does this give us? Now, cos of z is cos of ix, which we can write as a half e to the I times ix plus e to the minus I times ix. And multiplying this out, we recover a half e to the minus x plus e to the x, which is the same as cosh of x. Similarly, we can look at the sine of z. This gives us sine of ix. Substituting that into the expression off the top of the page for sine, we get 1 over 2i e to the I times ix minus e to the minus I times ix. This is 1 over 2i e to the minus x minus e to the x. And with a bit of manipulation, you can show that this gives you I times the sine of x. It's also easy to show that cos of x is cosh of ix, and I times sine of x is the sine of ix. So this shows the deep link between trigonometric and hyperbolic functions when you move to complex arguments. Next, we're going to talk about powers and roots of complex numbers. We're interested in functions like f of z is z to the n, and f of z is z to the 1 over n, where n is an integer. Now let's write z in modulus argument form. Then it's easy to see that z to the n is r to the n e to the I n theta, and z to the 1 over n is r to the 1 over n e to the I theta over n. Recall that we can write z in equivalent form as z equals r e to the I theta plus m times 2 pi, where m is an integer. And this came from the fact that if we rotate a complex number by an angle of 2 pi, we end up with exactly the same complex number that we started with. Now with this fact, we can then write that the nth root of z is given by r to the 1 over n times e to the I theta plus 2m pi over n. Now what does this mean? Let's consider when n equals 2, in other words, we're taking the square root of the complex number z, different choices of m will lead to 2 distinct values of z to the half. Each value has the same modulus, but arguments differ by pi. And in fact, the nth root of z is in general n valued, with successive values having arguments differing by 2 pi over n. The best way to see this is to consider a concrete example. So let's consider f of z is the cubed root of z. And let's say that z equals 1. Okay, so we can write z in modulus argument form with r equal to 1 and theta equal to 0, because it lies along the real axis. This means that f of z equals 1 is r to the 1/3, which is 1, and then we have e to the I, theta is 0, plus 2m pi, integer multiples of 2 pi, divided by 3. So we have e to the I times 2m pi over 3. And here we have m equaling 0, 1, or 2. If you do other values of m, you will in fact recover the same complex number as if you set m to either 0, 1, or 2. Now these choices of m corresponds to, well, if we let m equal 0, we have e to the 0, which is 1. If we let m equal 1, we have e to the 2 pi I by 3. And if we have m equals 2, we have e to the 4 pi I by 3. We can draw these in the complex plane. So when m equals 0, we have that the cube root of 1 is 1. So this is m equals 0. When m equals 1, we get an argument of 2 pi by 3, which lies over here. So this angle here is 2 pi by 3. And this is m equals 1. And we also have m equals 2. And that's a further rotation of 2 pi by 3. These vectors should all be of unit length. I'll put the points in as well. These numbers are called the roots of unity. And we will encounter them a lot throughout this course. As an extra example for you to try, try looking at the same problem, but for z is the imaginary number I, and compare your result to this one. The last thing I'm going to mention in this part is the complex logarithm. And I said earlier that we would revisit it. I'm just going to mention it briefly here, but we're going to look at it a lot more in topic 4 of the course. Just as we have extended the exponential function with real arguments to the exponential function with complex arguments, we similarly define the logarithm of a complex number. We denote this as ln of z, where ln means to the base e. And writing z in modulus argument form, we then get ln of r times e to the I theta. The logarithm of the product of two terms is the sum of the separate logarithms. But again, we know that theta is only defined up to multiples of 2 pi. So this is also given by ln of r times e to the I theta plus 2n pi, which is ln of r plus I theta plus 2n pi, where n is an integer. Now this is something very interesting. This means that the complex logarithm has an infinite number of values corresponding to all choices of n. We will revisit this multi-valuedness in topic 4. That's the end of part 2 of topic 1, revision of complex numbers. To summarize, from parts 1 and 2 of this topic, you should now be able to use the polar description of complex numbers. You should be familiar with Argand diagrams. You should be able to perform basic operations and arithmetic with complex numbers, and relate these to vector operations. You should be able to use and manipulate Euler's formula and Moivre's theorem. And you should also have some familiarity with basic complex functions like trigonometric, hyperbolic, exponential, and logarithmic functions, as well as powers and roots. You'll get lots of practice at these in problem sheet 1, so I encourage you to have a stab at as many of the problems as you can after watching this video.